Path Spider. Brian, I guess that's you. So the short papers again have 5 minutes. You can't ask questions, but the challenge is to do something to make them run over. Yeah, so whatever you can other than go into the microphone is fair game. All right, go.
Hi, I'm Brian Trammell. I'm talking about Path Spider. Path Spider, the 6-legged spider, it used to be an 8-legged spider, but then it hit a compression proxy on the way through the internet. That was Ted. That was a laugh for Ted. Thank you, Ted. So what is Path Spider? Path Spider is an active measurement tool for looking at path transparency issues in the internet. What is path transparency in the internet? That is the inverse of path impairment. Path impairment is I try to send a packet or a stream of packets and the path does something to them, like drop them or delay them because of some property of the packet. The reason we care about this is that the lack of transparency in the internet is the thing that basically makes it hard to do anything other than TCP circa 1984. The way that we measure this is like any active measurement tool. We throw a bunch of packets at the internet and then we see what happens. The ideal way to do this is if you actually control both the source and the destination, like so you send a bunch of packets through here. The green packets are the things you think are going to work. That's the A, and the B is the new thing. So the B is the A is the experiment, B is the control. These are the control packets. These are the experimental packets. You look at what happens at the source, you look at the destination, you send them back to the source, somebody coordinates on, you know, did I see the same thing at the front end and at the back end? This doesn't scale very well because you need to own a whole bunch of sources and a whole bunch of destinations. You can have relatively fewer sources and a whole bunch of destinations and then just essentially make inferences based on what happens along the path. Either the destination sends you back something that you can infer, hey, it didn't get the packet that looks like this, or the router does. Traceroute works like this, ping works like this. And then you can look from multiple sources at a single destination and you can compare things that happen from different sources in order to be able to compare what goes along the path. So the way that Path Spider is put together is we're looking at A/B tests that come from different system level configurations. So the original thing that we looked at was ECN, where you'd basically have to use a sysctl to either turn ECN on or off. You can also do things with looking at the various ECN, ECT, and CE code points by using packet mangling with IP tables. So there's a configurator that basically switches between configuration A and configuration B and configuration A and configuration B. And in the meantime, the workers basically synchronize with that and say, oh, I'm in configuration A, I'm going to run the A test. I'm in configuration B, I'm going to run the B test. We generally run a whole bunch of workers because 99.9% of the time, the workers are basically just sitting there doing nothing, waiting for things to happen on the internet. This is one of the few places where you can actually use 500 Python user space threads at the same time and do useful work. Then we watch what happens. The test traffic goes to the target, and there's a thing called an observer, which is basically just watching packets. It's a passive measurement of the active measurement traffic. And then we take a look at the traffic info, we take a look at the target info. If it comes off the workers, we merge them together, and that goes into output data, which goes into the Path Transparency Observatory, which you'll be hearing about in 15 minutes. We've used this to do a few things recently. We did explicit congestion notification again to the Alexa top million websites. We did a paper about this with an earlier version of Path Spider 2 years ago. It turns out we're still in the logistic curve, 2 to 3 nines of the time. You don't have any problems that would require you to fall back on ECN at all. And then ECN is now successfully negotiated 70.0005% of the time. We're excited to see that because the first digit was new. We've looked at differentiated services code point. DSCP of the internet's actually a little screwed up on the Alexa top 100K. About 10% of these are giving back unexpected code points, things that it's leaking internal use of the DSCP or private use of the DSCP. Looking at TCP fast open, TCP fast open is not as deployed as we'd like to see it. Google's doing a good job of it. There are a few sites that are not Google that are doing a less good job of it. And there's lots and lots of stuff that gets in the way of it. So we had a student do this, and the first thing that he realized was, oh, oops, ETH's network drops TFO. So he was like, oh, I'm doing this and my test doesn't work and this is broken and that's broken. And he was making the assumption that he was on a network, that the access network wasn't the problem. It was like, oh, oops, I am on an access network, it's the problem. Then he went home and he ended up that he was on the other side of some CPE that was that worked with TFO on v6 but not on v4, because all of the wonderful middle box stuff that they implemented was v4 only. If you want to play with this, go take a Debian machine, put it on testing, app install Pathfinder.
Whatever you did, it worked. No.
Questions later?
Questions at the poster.
Okay.
Next is Stephen, who has the blank easel over there. Or maybe it's just really small.
I have the contents of a poster. They're all in this laptop, so I will stand at the front when I'm done, and you can come and ask me questions. So I'm Stephen, I'm at Yahoo, and we have a lot of IPv6 traffic, and we measure that IPv6 traffic because it's now significant enough that it plays into a lot of things like capacity planning, where we do peering, how we do peering, and we pay attention to things like what our DNS load balancing is doing, because sometimes that can be pretty terrible. I put the two-pager together largely because people kept asking, when you look at the v6 deployment trends graphs, why does it look like there is more v6 at weekends versus weekdays? So I grabbed access logs from our CDN over a 3-week period. The gap in the middle is because I fat-fingered one day and deleted the whole day. But you see the broad trend. So if I look at the weekly, on the Mondays through Fridays, we are sort of hovering around about the 11%, serving about 11% of all of our requests over v6. And then we bump into the weekends and we hit about the 14-15% mark. So one of the things driving that largely is what the fixed line ISPs are doing in the US. I have better graphs in the paper, but if I aggregate a bunch of those ISPs together, one of the bigger drivers is that during weekdays, office hours, we see a bump of about an additional 25% IPv4 from those networks in particular, versus the IPv6 level, which is actually fairly constant, which might actually be things like these SAM-nose boxes, etc. But we get a lot of v6 traffic through the week from these ISPs, and it's all fairly constant. So the bigger thing around why does it look like there is more IPv6 at weekends, it's not, it's simply that there is more IPv4 on weekdays. Our daily cadence is also not stable, in the sense that if IPv6 deployment was uniform, that would also be fairly level. But we get these troughs at around about the 5% of requests per hour over v6, bumping up to about 20% per hour at the weekends. And that's largely based on where IPv6 is deployed today. So looking at the time zone, according to our geodata packs, of where IP addresses, HTTP requests are coming from, this is not the hour in which they were served. This is where the IP addresses are apparently located. We see the clusters on the, largely one cluster on the left representing the Americas, and then another cluster in the center representing Europe, those being the two primary clusters where we see actual IPv6 activity. The primary contributor here is definitely the US, where we see up to about 30% of requests served over v6 at weekends. So IPv6 eyes are primarily in America at home. Take from that what you will. If you have additional questions, I have all of the graphs on my laptop, and I will be here during the poster session. Thank you.
All right.
All right.
Well,
3 minutes.
this work is related to can we use the bits in IPv4 header or not? That is the question. Next, please. So ideally, we are using the IPv4 header to ask the network to provide some special treatment to the packet. So this work is, so we are looking at, so we want to see how the middle boxes behave with DSCP, ACM, EBL bit, and with the identification field, how the current internet responds to these bits. Okay, so our approach is like we send scene SYNAC packet. So we have server and clients. So, and the clients can be anywhere, but the server, we have 3 servers. So here the client sends a TCP scene packet with some certain DSCP value or ECN bits set like that, and the server responds with the corresponding packet, with another packet. So what we want to know is that we want to know the packet really passes or not. So we want to see if the packet are dropped by congestion. So we need to detect it that it is not dropped by the middle box. So for that, we are using this ICMP packet. We can use a TCP scene, other TCP scene. Basically, our idea is that that packet should pass in the internet. So that's why we're using ICMP packet. So what we are doing, we are sending TCP scene and ICMP, and if the packet is dropped because of the congestion, both will drop. If it is dropped by middle box, so ICMP will pass to the server. So in that way, we can detect the direction of a packet drop. So, and we repeated the test to keep it consistent about it. We repeated the test 3 times to see that it is dropping 3 times means it is a consistent drop. So, and right side, it was the locations where the clients run the test, and the servers are in Norway and one in Amazon cloud. So then we did the test. Next, please. So what we found, this is one of the results, like the DSCP values. So currently we refer to one draft that is related to the web browser setting the DSCP values. So what we see is that if the end user set certain DSCP values, and what we see is that some packets are dropping because of this non-zero DSCP values that we are seeing. And what we see is that also certain DSCP values is changing to some other unknown, unexpected value, which are not standardized. Even 0 is changing to some other value. So even those, and what we see also, this is the fraction of distinct paths, what we see from the client to server. And what we say is that using different DSCP values, we saw some drop. If we add the sum of the paths, it is not equal to what DSCP 0 passes. So in that way, we say that, okay, it is there is some drop. So we are following, if there is a drop because of some DSCP value, we should follow some fallback mechanisms. And we are giving the conclusion like that. And rest, and also another interesting is that EBL bit passes in the internet, and nobody did a test before that. So we are using the, and we saw that only 3 or 6 paths the EBL bit getting stripped, but rest of the path EBL bit is remain unchanged. So the question is, can we use these bits for other transport selection or any for future use? So that we are looking at it, and the rest of the, if anybody is interested, so I'm there, so we can proceed further. Yes. Thank you.
All right. All right. Final one.
Last one.
For this session.
Right. So, SM58. I feel like I'm back in the band. So Brian already explained to you what path transparency is, but I'm a security guy, so I have to be explained simple things, and I will explain them to you as well. Again, we are part of a project called MAMI, which is Measurement and Architecture for a Middle-Boxed Internet. We have 3 large areas: measurement, architecture, and experimentation. I'm in measurement, which means that all my slides are going to be slightly red. And so what is the problem that we're trying to address? Well, The simple view is this. So I thought I'm a security guy masquerading as a networking guy, so I call my stations Alice and Bob. And Alice and Bob are connected to the internet, which means that there are lots of routers in between. These routers are connected using some kind of network. And now Alice has a packet that she wants to send to Bob. And the idea is now that the network chooses a path and the packet is transferred along that path to Bob. And the interesting thing here in this particular slide is that the packet that comes out at Bob is exactly the same that one that went in at Bob. But in reality, that's not what happens. What happens in reality is that the middle boxes, the circles here, they change the packet, they change the headers. For example, they're NUT boxes or there may be load balancers and so on. So they change the headers or the packet in ways that the packet that ends up at Bob's looks superficially like the packet that went in, but it's not necessarily the same. And that's bad for two reasons. One reason is in order for those middle boxes to be able to manipulate those packets, they need to know what header fields they are, where they are, what they mean. That means they have to know the protocols. And that means that if you want to deploy a new protocol, middle boxes don't work anymore. And we want the middle boxes to work because they do good things for us. Second problem is related to the first problem. If you have ubiquitous encryption, then all the headers except for the outermost ones will be encrypted and therefore equally inaccessible to the middle box. So what are we going to do about it? So in our project, as I said, called MAMI, we have two large areas. The one area is trying to find out how bad is the problem. So to what extent do middle boxes manipulate stuff? And the second thing that we want to do is we want to develop a middle box cooperation protocol called MCP that allows the middle boxes to do their work with the full cooperation of the endpoints, making it explicit and thereby making the internet a better place, which is why we're all here, right? I'm working on the observatory, so we're working on the first goal. That means we have an observatory, a big database that contain observations about paths. Essentially, that means we know at a certain point we made a measurement along a certain path and certain conditions did or did not hold on that path. And we also want to allow path transparency measurements on a global scale. And to answer a question of one of our reviewers, why didn't you take one of the existing observatories? Well, there is no observatory in existence that we know of that specifically deals with transparency research, path transparency research, so we have to do our own. What kinds of questions do we want to answer? Well, the first question is, can we run the internet over UDP? Because if we can simply layer all the new transport protocols on top of UDP. And even though there's technically would be protocol ossification, it isn't as bad as it would otherwise be. Another question is, do middle boxes interfere with condition signaling? That is something that Brian has already talked about a little. ECN is one example of such a condition. This is also something that we want to look at. And the one other area is pure phenomenology, i.e. we are curious, do paths remain stable? Do middle boxes appear and go away? Or do all of these middle boxes appear on the same paths? Now, you may be wanting to know, why should you be interested? Well, one of the things that we can do, we will be doing, is a part of our observatory will be publicly available, and you will be able to run special queries on our data, and you will be able to see interesting stuff. That concludes my presentation. Therefore, come and see our poster. Thanks.
All right, thank you. That's all of the short papers. As he says, go see the posters. We'll restart about past.
Right.